to Utah.
I see.
I think we're getting ready to stream here. Okay, got it.
Yeah, looks like that way.
Profesor,
I will start. ¿Estamos listos, Carlos?
Sí, profesor, estamos listos.
Okay, Professor, I will start first in English and then in Spanish, okay?
No problem.
Carlos, ¿estamos listos? Yes?
Estamos listos, profesor.
Okay. Good afternoon, everyone. Welcome to one of the last seminars of the year. Today, again, we have a great speaker. We have Dr. Rathje here with us. Dr. Rathje is there with a great background from University of Texas, Austin, and she will be speaking today about the seismic risk assessment for slopes and dams. I'm going to speak briefly now in Spanish, Professor. Hola, ¿qué tal? Muy buenas tardes a todas y todos. Bienvenidas y bienvenidos a este nuevo seminario de geotecnia de la Universidad de Chile. Este es uno de los últimos seminarios de este año y hoy día tenemos nuevamente una invitada de lujo. Tenemos a la profesora Rathje de la Universidad de Texas en Austin, a quien ustedes pueden ver ahí con un background de la universidad. Me voy a cambiar al inglés ahora para continuar con nuestro seminario. Professor Rathje, hello, how are you? Good afternoon.
Hola, ¿qué tal?
Todo muy bien acá. How is life back in Texas?
Well, Texas is doing very well. The weather is great. And the football team is not doing so well, but we now have a professional soccer team in town. So there's lots of good stuff going on here.
Okay, are they doing better than the football team?
Actually, no, they're bottom of the table, but we have we have a soccer team. That's number one.
Well, sometimes happen. It's fine. It's fine. It's cycling. It's cycling.
That's right. That's right. It's their first year in the league, so we weren't expecting much.
I see. Very well. Professor, before starting this great talk about the seismic risk assessment for slopes and dams, I wonder if we can make you some 3 quick short questions. The first one, how Professor Rathje became Professor Rathje? Where did you do your undergraduate? What did you do after that? And how has been your career through this up to this point?
Great. Well, I'll try and keep it a little bit short, but I think I had a bit of an interesting path. I'm from New York originally, and I did my undergraduate studies at Cornell, but interestingly, growing up, I always wanted to be a journalist. I knew nothing about engineering. And just during my senior year in high school, I realized I liked math and science better than English and writing. And so I had a teacher who encouraged me to consider engineering. And having lived near New York City and seeing all the big bridges and buildings, civil engineering was what interested me. And so that's why I applied to Cornell and studied at Cornell. So throughout my undergraduate studies, I thought I wanted to do structural engineering. And so you're going to see a pattern here of indecisiveness, because when I was a senior, again, in college, considering graduate school, I got to the point where I actually applied to all of my graduate schools in structural engineering. But at the same time that I took steel design, I took foundation engineering from Fred Kulhawi at Cornell. And I realized I just really liked foundations and geotech as opposed to structures. So I had to call up all the schools and ask them to move my applications over to geotechnical engineering, which they did. And so I ended up at the University of California, Berkeley for my master's and PhD. So I think one lesson to be learned there is it's never too late to make a change. The sunken cost fallacy, the idea that I've already gone so far down that path, don't be afraid to change, because it can just change, what you're doing how much you enjoy it.
I
So
agree.
I was at UC Berkeley until 1997. And then I started here at the University of Texas in January of 1998. So I'm coming up on 24 years here at the University of Texas. I know I don't look old enough to have been 24 years
God.
anywhere, but
Time flies.
it does. I know it does. Absolutely. So, and yeah, so I've been at the University of Texas since 1998 and have some great colleagues in geotech and across the department, and super happy to be here in Austin.
Nice, very nice. And what are your current projects, Professor? What are you working on these days? Do you have a lot of students?
So there's several kind of areas that I've been working in more recently. I would say the biggest chunk of my time is dedicated to the design safe cyber infrastructure, which is a huge project to provide a data repository and cloud-based data analytics to the entire natural hazards research community. So it's not just supporting geotechnical research, but all types of research related to earthquakes, hurricanes, et cetera. So I'll mention Design Safe a little bit in my talk, just in terms of some of the data we've published there. But I'd love to encourage anyone here to take a look at designsafe-ci.org. It's open to anyone around the globe for data publishing. You can have some access to OpenSeas to run some analyses on the supercomputers. So Design Safe and enhancing the capabilities and promoting it is a big chunk of my time. Now, that's not necessarily enabling my research, but it is enabling the research of many around the country and around the world. Another thing I'm working on is induced seismicity. In Texas, we have, I didn't think 22 years ago when I came here, I'd be studying earthquakes in Texas, but due to the oil and gas activities here in Texas, we're involved with the Texas Seismological Network to understand the causes of seismicity in Texas that have been accelerating, and then also the accelerating risk to infrastructure and people. So that's been an important part as well. And then, you know, I've been doing seismic slope stability stuffs. Obviously, that's been a place where I've done a lot of work for many years, and that's continuing to evolve. Also, site response analysis, so looking at ground shaking estimates using site-specific site response analysis, in particular related to critical facilities like nuclear facilities, and bringing in all the uncertainties into that analysis. So that's kind of the places I'm working these days. Nice,
nice, very nice. And with so much geotech and so much earthquakes and interesting stuff, is there time to do a hobby or something that you really like doing in your spare time?
So I would say, you know, my spare time is split between watching sports. You could already tell. I already talked about Texas football and soccer here in Austin. We're season ticket. My family and I are season ticket holders to the Longhorns, is also to the Austin FC football club. But we all follow Chelsea. That's our main soccer club out in the UK. So we're very happy they're top of the table over in the UK. So sports is a huge part of our lives.
Nice.
My daughter plays soccer in a pretty competitive league, so we're always driving her somewhere for soccer. And then I just, you know, like to exercise, whether it's walking or biking, things like that. And then I would be remiss if I didn't mention that my son is a tuba player in the marching band at the high school. So I spend a lot of time watching marching band competitions, which is a lot of fun.
Nice. Very, very nice. Very, very nice. Thank you very much for sharing that, Professor Rathje. Well, I will close my microphone, my camera, so you can share with us your expertise and knowledge on the seismic risk assessment for slopes and dams. Thank you very much again, Professor. Thank you.
Great. Thank you, Felipe, and thank you everyone for attending the seminar today, where I'll talk about the seismic risk assessment for slopes and dams. And of course, I'd be remiss if I didn't acknowledge the people who really do the work. And in this case, it was my former student, now postdoc Young Q Cho, and then my current PhD candidate, Jingwen Hu. So when we think about seismic risk assessment, and I really want to focus on the fact that we're talking about risk assessment, not just probabilistic assessment of, say, movements or whatnot, is we're trying to actually evaluate the probability of damage given ground shaking. And damage is somewhat of a qualitative concept. And so often we talk about different damage states. So you can see here, we might be talking about minor versus severe damage. And the main tool that we use in these assessments is what's labeled here a fragility curve. And I think the structural engineers have really taken a good use of using these fragility curves. And I think geotechs, we have some to learn on how to apply these concepts to what we do. So for instance, here, this fragility curve relates the ground shaking intensity, that could be peak ground acceleration or peak ground velocity or some other intensity measure, to the actual damage, the probability of experiencing a specific damage state. So you see at or at a certain intensity, there may be a low probability of severe damage, but a higher probability of minor damage. And it's these fragility curves that allow us to really evaluate the risk. Now, when we try and apply this to our problems, in this case, the seismic performance of slopes and dams, we know that the common way we evaluate performance, not damage, but performance, is through movement. So you can see here's a slump from an earth slope. So we might try and predict the displacement. In an earth dam, we might predict the settlement. So in these cases, we typically want to know under the level of earthquake shaking, what type of seismic, co-seismic movement will be induced by the ground shaking. Now, traditionally, for many decades, we've used the sliding block approach to do this evaluation. And in that case, we look at the slope and we find a critical failure surface and define KY, the yield acceleration for that sliding mass. And that yield acceleration represents the horizontal force that, when applied to the sliding mass, results in a factor of safety of 1. So the idea being that any acceleration or force bigger than KY results in a factor of safety less than 1, and therefore movements. So we take that yield acceleration and we idealize it as a sliding block, sliding down an inclined plane, so that now we have accelerations going in to this block with a yield acceleration. And then, as I mentioned, we may have a yield acceleration. Here's our earthquake motion. And on each of those excursions beyond the yield acceleration, we get some downslope movement. And ultimately, it's this downslope movement, in this case, a little over 20 centimeters, that we use as an indicator of the seismic performance of this slope. Now, as many of our analyses do, we have to employ several assumptions. In this case, the two main assumptions we bring into this is that all deformations and movements are localized on a well-defined slip surface. We're essentially assuming it's all along this failure surface, or in this idealization, along this inclined plane. And then the second assumption is that movements only occur when the strength is exceeded, because KY represents when the strength is mobilized. And so if the strength is not exceeded, we have no movement at all. Now, when we do these analyses, we have to make some assessments of the sliding mass itself. The geometry and engineering properties of the slope go into assessing the yield acceleration, which I already introduced. So that represents the resistance or the seismic resistance of the slope. But we also want to understand or incorporate the dynamic response of the sliding mass. And so we typically use some sort of natural period to do that. I traditionally have used the initial period of the sliding mass, represented by 4 times the thickness of the slip surface, divided by the average shear wave velocity. So this kind of uses that one-dimensional assumption in assessing that dynamic response. Of course, this analysis then also requires some estimate of ground shaking. And of course, when we worry about ground shaking, we always have to incorporate not just the intensity of shaking, but I'm a big believer that frequency content plays as big of a role as intensity, and then duration also can come into play. So when we look at predicting displacements, and throughout this talk, I'll use capital D as representing displacement. I'm sure many of you are aware of the empirical models that have been published. These really are, you can think of them as surrogate models. They allow you to predict the displacement as a function of these various parameters without actually having to run the sliding block analysis yourself. So they're a surrogate for doing the full analysis, which requires a lot more work. You've got to pick ground motions, you've got to do your dynamic response calculations, et cetera. So in some ways, we do all the hard work for you and then develop statistical models that predict displacement. And there are many that have been published. There's two just listed here, kind of John Bray and his group, as well as the work that I've done since working with John many decades ago now. Now, of course, we are in the 21st century and we're moving more and more towards stress deformation analysis. So this could be finite element or finite difference analyses. So we take our slope and we create a finite element or a finite difference mesh, and we put our earthquake motion in the base, and then we can compute the displacement at the ground surface of the slope. And I would argue that is really what we care about, because typically what we're worried about damaging is actually at the top of at the ground surface. Some of the benefits of stress deformation analysis is there is no assumed slip surface. So we don't have to make any of those assumptions. The deformations do not need to be localized. So, the two main assumptions I mentioned earlier don't need to be employed. We can more rigorously incorporate the nonlinear stress strain response, and we can accumulate movement not just during failure, but due to the nonlinear response before failure. So for all these reasons, people are tending towards stress deformation analysis. So with that kind of background, I want to focus on kind of two main topics within this idea of looking at the seismic risk assessment of dams and slopes. So first, I kind of want to expand on this fragility framework that I mentioned as applied to earth slopes and dams. So I'll kind of introduce what people have done in structural engineering and how we can adapt it for earth slopes and dams. And then an important part of that fragility framework is predicting those deformations through these type of surrogate models that I introduced. So I'm going to talk about some of the more recent work we've done, just recently accepted in Soil Dynamics and Earthquake Engineering and almost accepted in the ASCE journal, where we used finite element analyses to develop a suite of displacements that we then performed classical regression, kind of similar to the Bray and Travisoro or the work that I've done with Antonakis, so that classical regression analysis. But we're also really trying to dabble into these new AI and machine learning techniques. So talk about a model we developed using an artificial neural network, and importantly, kind of comparing and contrasting the performance of these different statistical techniques. So let's talk about the fragility framework first. When we start dealing with fragilities, the first thing we have to do is to identify the engineering demand parameter that's going to be pushing the system towards damage. Importantly, this engineering demand parameter, EDP, must be computable. You must be able to compute it from an engineering analysis because we need to be able to assess it. And of course, it must be relatable to the damage state. And for instance, the damage state in a building may be the level of cracking. And all of these things depend on the system that you're considering. A building should not be analyzed like an earth slope, but it's still useful to see what the structural engineers do. And so, for instance, where cracking may be the damage state that they're interested in, they found that interstory drift is the engineering demand parameter that relates best to cracking, or at least relates well to cracking. And so they'll run analyses about interstory that compute interstory drift and relate that to the damage level. Now, of course, once we talk about slopes, interstory drift doesn't mean anything. So in dams, commonly what's been used is relative settlement. So the settlement of the crest relative to the height. And in slopes, we've used permanent displacement D, although you could argue that even that displacement, how you should represent it relative to the settlement, I'm not sure many of us have really gone through the rigor of trying to assess how that actually relates to damage. So going back to the fragility framework, there's really two main components, and it all relates to this engineering demand parameter. So first is the seismic demand model, and that takes the intensity measure, again, peak ground acceleration, something like that, and predicts that engineering demand parameter. Okay, so we're trying to go from ground shaking to this relative settlement or interstory drift. The seismic capacity model then takes that engineering demand parameter and predicts the probability of the different damage states. Okay, so this is trying to understand how does, for instance, interstory drift relate to different levels of damage in a building, or in our case, damage in a dam. The surrogate models I've been talking about, and I think this is where the geotech world has done a really nice job. We've spent a lot of time on these surrogate models, and I'll spend a lot of my talk today as well. But I want, the part we haven't done such a good job with is to how do we put those together, including their variability and uncertainty, with the demand and capacity to put that together into the fragility model. Because remember, the fragility model goes from ground motion to damage. And the engineering demand parameter is kind of the mechanism that makes that relationship work. Okay. So this is what we ultimately want. And so doing a little bit more work of integrating a capacity model with the demand model will get us there. So we recently did some work on evaluating capacity models for dams. And we published it in the Lifelines, ASCE Lifelines conference that was supposed to take place last year, but will take place in January in LA. And we developed this based on field case histories. The Pels and Fell and Sway's Good case history databases on dam performance are really, really excellent. They have 80 dam observations of dam damage with records, importantly, of the relative settlement, as well as the original author's assessments of the damage state. Is this moderate damage? Is this minor damage? As well as the crack widths that they observed. So the damage states that we took from these data was we set things in minor, where the crack widths were less than 5 centimeters. We took the dams that had crack widths between 5 and 20 and called those moderate damage. And then the serious were 20 centimeters and above. And we used their data to come up with some capacity models. And I'll quickly explain how we did that. It's actually relatively simple. We have 80 dams, and for each, and we know their damage state. So for each damage state, so let's say the moderate damage, for every 80 of those 80 dams, it either experienced the damage state or it didn't, right? So there's no probability in between. It's either 0 or 1. It either did or it didn't. And then each of those dams, we have the actual value of relative settlement that was observed. So we plot these data, and clearly the dams that did not experience moderate damage had smaller relative settlement, but some of them had a little bit on the higher level. And the ones that did experience moderate damage are mostly on the higher end, although there is a little bit on the lower end. And that's what makes it uncertain. And that's why this probability starts slow and slowly comes up and then hits 1 up here. And these black points basically represent the average between the zeros and ones in each of these different bins. And so we were able to do this for the 3 different damage states we defined. Now, traditionally in geotech, we like thresholds. We don't like probabilities like this. And in fact, that's what Pels and Fell and Sway's Good did with essentially the same data. They said, well, for moderate damage, 0.2%, less than 0.2% is not moderate. Above 0.2%, you do get moderate damage. And they felt they needed an absolute threshold. But that essentially represents this type of boxcar fragility curve, or not fragility curve, I should say capacity curve or cumulative probability curve. But clearly, some of the dams less than 0.2 did experience damage, and some above 0.2 did not experience moderate damage. And Sway's Good did something similar, but they used a different threshold. They used 0.5% of relative settlement. So this expands and enhances what had been done by these in this previous work by considering the fact that there is uncertainty in assigning the damage state at a given value of relative settlement. And we did this for 3 different damage states, as I mentioned, and this was published in our paper for the conference, and you can learn a little bit more about it there. But what you see here is for minor damage is much further to the left. Okay, so that means that a lot less settlement is needed to get just your minor damage, a little bit more to get moderate, and then a bit more to get serious. And in fact, these two are more similar to each other than the minor damage. And just to show you a simple example of how I can use that capacity relationship, that's not a fragility curve, it's a capacity relationship. But I can use it to develop a fragility curve for a specific dam, is shown here. And again, this is also in the paper. So let's say I have a dam of 15 meters high. Its yield acceleration is 0.15 G. I'm going to do this all within a sliding block framework. We've got uncertainty on the KY, so I'm going to put a sigma there. And the demand model, the surrogate model, I'm just going to use one of my displacement models that I published more than a decade now ago with Gökhan Sayli. And we are going to make the assumption that the displacement that comes out of Rathje and Sayli, which would be, I would assume, would be on a slip surface, can be used as the settlement at the top of the dam, which is an assumption. But we're going to calculate the relative settlement from that demand model. And we're going to just consider a range of PGA values from 0.01 to 1G. And we're going to combine that with the capacity models that I just showed you on the previous slide. So relative settlement will go into here, and then that'll allow us to get the probability of the damage being exceeded. And the details of there needs to be some Monte Carlo simulations in this arrow. So arrows are never as simple as they seem on the slide. But by taking the variability uncertainty here, including the uncertainty in KY and the uncertainty in the capacity of the dam, you can then develop a dam-specific fragility model, which in this case would say for this dam, at 0.4 G, for instance, here's the probability of serious damage, here's the probability of minor damage. So clearly, serious damage should have a lower probability than the lower damage state. So this is a very useful graph to have, because if an earthquake happens in your area and you get your shake map from the geological survey, and you find out the ground shaking at your dam was 0.2 G, you may say, you know what, I'm not too worried. But if it starts heading up into this zone, you should start being a little bit more concerned. And if you can apply these fragility models to your entire inventory of dams, let's say you're a dam owner, you can very quickly prioritize which dams you need to go inspect. So the rest of my talk is going to focus on the demand models, because I had to make some big assumptions in that previous analysis to go to the fragility model. So I'm going to talk about how we can do better in terms of predicting movements of slopes given ground shaking intensity. So this is when we'll move to the second part, where I will talk about our classical regression as well as our ANN models, which are based on the finite element study. So we developed 49 finite element slope models that we analyzed. We varied many of the parameters. So you can see we basically have a single slope here. The height of the slope was varied between 15 and 30 meters. The depth of soil beneath the toe of the slope was varied. So sometimes it went deeper, sometimes it stopped right here. We did different slope angles of 20, 30, and 40 degrees. We assigned different strengths, either C-phi combinations or phi equal to 0. And we varied the shear wave velocity between about 200 and 400 meters per second. So this material here is the main slope movement, or I should say the layer where the slope movements are associated. We do have a stiffer layer, which is given a stronger property, so there isn't much movement there. And then we have a bedrock layer, and then we apply the shaking with a Leismer dashpot at the base. Now, it's a lot harder to run finite element analyses and do suites of properties as opposed to what I did previously with sliding block analysis, where I just say, oh, KY is this. So here we had to think about how are we going to model the stress, strain, strength properties of the materials. So we had some phi equal to 0 materials with different cohesion or undrained shear strength. That should lead to deeper sliding surfaces. We would have some kind of moderate cohesion and friction angle values, so that kind of in blue. And then we had some low cohesion, high friction angle materials, such as shown here. And those would tend to have your shallower slip surfaces. And then as the strengths went up, we generally increased the shear wave velocity. We ran all of these analyses in LS-DYNA. We ran them on the supercomputers at the University of Texas, at the Texas Advanced Computing Center, through an allocation provided by DesignSafe. So again, this all kind of fits in with the DesignSafe framework, as I mentioned earlier. We use the hysteretic soil model that's available in LS-DYNA, where the stress strain curve is assigned based on a backbone G over Gmax curve. So it gives you a lot of flexibility for assigning the stress strain properties. So as I mentioned, we analyzed 49 slope models. And of course, we were not going to just run a slope model without doing your traditional limit equilibrium analysis, because that's really how we think. And so for each slope, we ran a limit equilibrium analysis. We defined its yield acceleration, and we looked at its slip surface, and we defined the maximum thickness of the slip surface, which we called H slip. And so in varying our properties, we wanted to get a good distribution of KY. So this plot here shows the range of yield accelerations and period of the slip surface, which is defined here based on the shear wave velocity and the thickness of the slip surface. And you can see we've got KY values as low as about 0.025 G up to about 0.5 G. We've got sliding mass periods from about 0.05 seconds to 1 second. So we're trying to really hit a range of slope parameters. We did ultimately find out that the slip surface was not the only parameter of interest. So we also are going to look at the period of the slope as a whole, which is represented by the slope thickness here. And you'll see me talk about H ratio, which is the ratio of the slip surface thickness to the slope height. So for small values of H ratio, that means we've got shallow slip surfaces like this. Okay, so that'll be a small H slip relative to the slope. As H ratio gets bigger, we're talking about deeper slip surfaces because H slip is large relative to H slope. So you'll see I'll talk about H ratio as well. Of course, if you know any of my work, you know I'm big into understanding ground motion intensity measures. And so one of the outsets, what we wanted to do was identify the intensity measure that was the most efficient and proficient in predicting displacement. So we considered peak ground acceleration, peak ground velocity, Arius intensity, cumulative absolute velocity, and because I love frequency content so much, the mean period as well. So 4 different intensity measures as defined here. We started with we ultimately ran more than 1,000 input motions through every slope. We started with 898 motions from Hale, who did her PhD at UC Berkeley with Norm Abrahamson. And we supplemented that by scaling some of the motions up to make sure we get some high intensity motions. So you can see here's the magnitude distance distribution of those 898 motions. So everything up to almost a magnitude 8. And these are really just shallow crustal events. Down to a magnitude 5, distances out to about 200 kilometers up to less than a kilometer. It's really hard to show plots of all the different ground motion intensity measures. So one way we settled to do that is we plotted all the intensity measures versus PGA. So each point in this plot represents a single ground motion. And this is the PGA for that ground motion, and that's the associated PGV for that ground motion. Okay, so first thing you realize is there's a lot of correlation between different intensity measures. Bigger PGA means bigger PGV. Bigger PGA means bigger areas intensity. The same thing with PGA and CAV. Interestingly, mean period, and maybe not interestingly, if once you understand what mean period is, there's almost no correlation between PGA and mean period, because this is a real independent assessment of the ground motion in terms of frequency content that has nothing to do with how intense it was. So having said that, what you can see here is we got a wide range of intensities. PGA from 0.01 G to 2 G, peak ground velocities less than 1 centimeter per second to 200, 300 centimeters per second. The red points are the ones that we scaled, so we were sure to get the highest intensity motions. So again, a broad number of motions. But now we're running 49 slope models, 1,000 motions each. So we've got over 50,000 analyses. That's why we use the supercomputers. So of course, you don't want to just trust what comes out of the slopes of the finite element analyses. We did want to kind of make sure there was consistency in terms of the displacements, at least the displacement patterns we got from LS-DYNA compared to what we would expect from pseudostatic analysis. So what's shown here at the top, these two slope models have friction-dominated strengths, so they should have shallow slip surfaces. The black lines represent the slip surface from pseudostatic analysis, and the colors represent the displacements for a single ground motion. So the actual value is not relevant. The key is the red is the largest. And so you can see that the displacements are concentrated shallow, as opposed to these two models where the strength was cohesion dominated, which should push your failure surfaces deeper. Again, the black are the failure surfaces from the limit equilibrium or pseudostatic analyses. And you can see the red is concentrated deeper now when we see that. The one thing, so I would say the maximum displacements are consistent with the pseudostatic slip surfaces. But one thing to notice that was a little surprising was for the shallow failure surfaces, how much displacement was happening below the slip surface. And this is going to lead to some interesting trends when we start looking at the statistical analyses. So how do we now take these 50,000 displacement values and come up with a classical regression analysis to predict displacement? What we did first was we had to identify which intensity measure best predicted displacements. And the way we did that is we looked at each slope independently first, and then before we started combining things together. So this is for one specific slope that has a KY of about 0.2 G, a period of about 0.05 seconds. And these are for the 1,000 plus ground motions, displacement as a function of PGA, PGV, areas intensity, and CAV. And we just fit, this is log, we just fit a straight line through the data. First thing you notice is the least scatter in the data is for peak ground velocity. So the scatter in these black points vertically is much less than any of the other models. And in fact, that's borne out with the sigma of the natural log of the displacements for the different regression models, almost 0.8 for PGA, 0.412, or excuse me, about 0.42 for PGV, over 0.6 here, over 0.8 for CAV. So this starts to show you that PGV may be a good player, a good candidate for our intensity measure. We did the same thing with combining intensity measures. So I'm not going to show you can't really show the three-dimensional plots, but we did the same type of regression using combinations of intensity measures like PGA and PGV, PGA and mean period, and just computed the sigma to see how they compared. And again, we did this for each of the 49 slopes. So what I'm showing here is sigma for the different models that use different ground motion parameter combinations or intensity measure combinations. And each point here represents one of the 49 models, okay? So the fact that there's many points here, it means that every model had a slightly different sigma. And the X's represent the averages. Now, if we just focus on the one intensity measure models, which is essentially what I showed you on the previous slide, you see that PGV wins, right? Everyone else is in the point above 0.6 and PGV is at 0.4. What's surprising is when we went to the two intensity measure models, almost nobody could beat PGV. Areas intensity and mean period got a little bit lower, but look at how different. It depends on which slope you have, whether it worked. There's a lot more variability from slope to slope on that standard deviation or variability. So in the end, we said PGV wins, not only because it was similar here, but if you're doing any type of probabilistic analysis, it's much easier to predict a single ground motion parameter as opposed to two ground motion parameters and having to consider how they're correlated with one another. So everything else I talk about today will use peak ground velocity as the intensity measure. So now, how do we develop the functional form for that kind of classical regression model? Again, we started with slope-specific fits to data. So this is, again, one slope. And for each slope, we did this linear fit, but we considered the intercept and the slope. And we wanted to see how the intercept and the slope of this regression, not a geotechnical slope, the slope of the regression, affect or change with KY, T-slip, T-slope, all those slope parameters. Because in the end, I want you as an engineer, just all you need is KY and T-slip, and my equation will give you the display and the peak ground velocity, and you'll get displacement. So let's first look at A naught, which is the intercept of this linear relationship. And so now I'm plotting A0 versus yield acceleration, and in this case, T-slope, not T-slip. And one thing we realized was that we got very different trends in the data when we dealt with deep slip surfaces with large H ratio. Remember, that's the thickness, the ratio of the thickness of the sliding mass to the slope. So this is basically deeper sliding masses, and the red circles represent shallow sliding masses, which H ratio less than 0.6. So you can see for the deeper sliding surfaces, A0 very clearly decreased with KY. Makes sense. KY goes up, displacement goes down, and we see it very clearly here. And in fact, that's how we modeled it. We put a linear relationship of A0 as a function of the natural log of KY. But it didn't do the same for the shallow slip surfaces. And so in this case, we had to we had to consider not only KY, but also T-slope, because we saw that T-slope mattered. And part of that is because you saw all that movement that was happening below this critical slip surface. And because of the distributed shear and getting enough shear stress in below the slip surface, we're getting movements. The dynamic response of the slope itself, nonlinear response, contributes. So for the shallow slip surfaces, we made the A0 a function of both KY and T-slope. We did something similar for A1, which is the slope of this relationship. And we found that, again, the deeper slip surfaces were much more well-behaved. A1 increased with KY. And then, but for the shallow slip surfaces, there was actually quite an interesting kind of a second order parabolic relationship, which we think has to do with some dynamic response of the slopes. So we incorporated that. So again, this is a paper that we're just finished, just under review again for the second round after revisions. And we have all the model parameters that will predict displacement as a function of PGV, KY, T-slope, and then H ratio, all of which you can get from a limit equilibrium analysis and a known shear wave velocity of your site. So that's how you can predict the average displacement. Of course, any probabilistic analysis and statistical model should also consider the standard deviation. And so we want to look at the variability in those predictions. We know from here that every motion with the same PGV does not give you the same displacement. So we need to quantify that variability. We did that by first looking at the total residuals for the model, which means we take the displacement predicted that we computed from LS-DYNA, from the numerical simulation, minus what was predicted from our model. And this is just represents for any slope I and motion J. And so we take the difference between those two, and that is our residual. So hopefully, if we have an unbiased regression, our average residual will be 0. And in fact, that's what we have. But you can see that the residuals from motion to motion and slope to slope vary considerably. So each point here essentially represents a motion. And then you see these vertical lines. And that's because each of those represent a different slope with a different KY, or a different slope with a period, different slope period. Okay. One thing that we did, which I think is unique, and we kind of borrowed this from ground motion prediction equations, is we took this residual, instead of just computing a big sigma, we partitioned it to the between slope sigma, or between slope variability and within slope variability, with the idea is how much of the variability is because we're not modeling a specific slope well, versus how much is just from motion to motion variability. And then we combine those two, the tau, which is the between slope variability, and then the phi, which is the within slope variability, to get the total sigma. So, and I should mention these red circles and green stars represent the average residual for each slope. So there's 49 points here, 49 points as well here. Notice every slope is not right on 0. If every slope had an average residual of 0, tau would be 0. There is no between slope variability. Every slope is predicted perfectly, but they're not. And so we take those red and green points, and we can kind of zoom in. We can call those eta, which would be the mean residual for each of the 49 slopes. And we calculate the standard deviation of these eta values, and it's 0.14, which is actually pretty small. And we saw no systematic variation with slope parameter, which is good. That means we're not biased for any type of specific slope geometry. And then the remaining variability is computed by taking that total residual and subtracting the mean residual for that slope, and then that's the remaining epsilon. We calculate the standard deviation of those epsilons, and that gives you phi. And you can see, we saw in this case, the phi was almost always right around 0.4, although it varied a little bit with T slope and a little bit with KY for the deeper slip surfaces. So again, we have a model for phi. And so the phi and the tau get combined together to represent the sigma for your slope. So what do these type of model predictions look like? And so what's shown here, because this is kind of ultimately how you would use them, is what type of displacement is predicted as a function of KY and T slope and H ratio for different values of PGV. So here I've plotted displacement versus KY for PGV of 20 centimeters versus, and the second plot is for 100 centimeter per second. And so let's first look at the deeper sliding surfaces, H ratio greater than 0.6. So we can see that as KY goes up, displacement comes down, and in this case, about an order of magnitude difference in displacement, okay? If we look at the shallow slip surfaces, remember the KY didn't matter as much when we were looking at A0. T slope mattered more. So interestingly enough, and we're still trying to sort through the details of this, but we feel that it does represent the deformation of these slopes. What you see here is for a small slope period, say 0.3 seconds, this would be the displacement. Here's the displacement for 0.45 seconds. Here's the displacement for 0.6 seconds. And KY only has a very modest effect on the displacement. Okay. And you see a similar response at 100 centimeters per second, but of course, all the displacements have moved up. One other thing that's shown here is a prediction from a model produced by Fotopoulou and Pitilakis, where they ran FLAC analyses of slope, so very similar to our type of analysis, doing stress deformation analysis, but they used a more Coulomb elastic perfectly plastic model. So there was no pre-failure yield or distributed shear deformation below the slip surface, which we think is affecting the results for our shallow slip surfaces. So what you see in their analyses for lower ground motion intensities, they tend to be smaller than our deeper slip surfaces. And they couldn't model the shallower, necessarily the shallower slip surfaces, although they had a range in there. But they're below this because it was elastic, perfectly plastic. So, you don't get displacement until the soil yields. And then at higher ground motion intensities, in fact, they're higher. And that tends to be because once it failed, it didn't continue to strain harden, but it was perfectly plastic. So there's consistency here, but differences because of the details and how the stress strain properties were modeled. So with that description of our kind of classical regression model, I did want to move on and talk a bit about what we've been doing with artificial neural networks. And so I'll give you first just a little bit of an introduction to ANNs, talk about how we split the data into training versus testing, how we developed the ANN model and did our regression analysis, and compare that model to the classical regression model. And this was just recently published in Soil Dynamics and Earthquake Engineering. So here's a schematic diagram of an artificial neural network. And the key thing is we've got these neurons in the middle and hidden layers that are going to relate input nodes to outputs. And so again, as you've probably heard of ANNs before, and this is kind of mimics the way a neural pathway would work in a biological system, where these inputs go into these nodes and in a complex way, and then feed out the other side. The question is, what do all these arrows mean, and why, and how do they work towards developing a predictive model? So in our case, if you look at how the inputs feed into the hidden layer, you've got your inputs, and it's actually relatively simple. You're going to multiply each input by an appropriate weight. So these are the weights that are associated with each input. So you multiply the weight times the input, sum them all up in the summing junction, add the bias to calculate a number z. You put the z number into an activation function, which then outputs something that goes right into this neuron right here. And so all the inputs are going into each one of these, and the weights are different depending on which inputs are going to which neuron. When you get to the other side, the outputs, it works very much the same. Now you've got these values of y in the middle. There's another set of weights, another bias, another activation function that predicts the displacement. So in our case, kind of similar to regression, we've got our inputs, ky, t slope, h ratio, come in the left-hand side. We give the model the displacements on the outside, and the ANN defines all the weights and biases that do the best fit to the data. And the key is there can be complex patterns in the data that are hard to model in a traditional regression approach. And the power of the ANN is the flexibility of it to find those patterns in the data and then model them. So in our analysis, we use the training data to derive the weights and the biases, as I mentioned. Now, one thing that we rigorously do in this type of analysis, which we should probably do more of in classical regression analysis, is to hold data back. So we call that the testing data. It is not used in the training. And we use it to select some of the things I kind of glossed over, like how many hidden layers. You can have more than one. How many neurons in the hidden layer? What's an activation function, and which one should I use? So we're going to use those to pick those values. But even more importantly, we use the testing data to evaluate the model that was developed with the training data. And it ensures that the model is generalizable to other data. You know, you've probably seen those plots where someone, you know, has variable data and they just put a huge spline, you know, a high order spline through all the data. It goes exactly through every data point, right? Perfect match. But you add one other data point and all of a sudden it doesn't fit that data, right? That's called overfitting. And the same thing can happen in this type of analysis. By using the testing data and evaluating the model on the testing data, it allows you to avoid this overfitting where you're fitting data that's trends that are only in the training data and are not generalizable to the entire data set. So when we looked at our data, remember we've got 50,000 plus data points. You typically take about 70 or 80% for the training and then leave out 20 to 30 for the testing. So we decided to go 70-30. And typically you just randomly select 70 and you randomly select 30. But in our case, we didn't want to do that for a very specific reason. If you have a model, a specific slope model, and you take 70% of the ground motions and put it in training and 30 in the testing, we know those points are correlated to one another. So your testing data is correlated to the training data. You saw those, you know, points where I plotted displacements versus PGV. Everybody's already on this trend. So we felt a better way to test our model was to actually manually select subsets of the data where we divided across slope models. So we took 70% of the 49 slope models, and we called those the training slope models. And we used all the ground motions for each slope. And then we took 30% of the 49 slope models. Those are the blue triangles. And this is just showing in KY, T-slip, and all the different input parameter space. So we did 30% of the slope models and left them out and used them in the testing. And to select the 70-30, we wanted to do it intelligently. And so that's why we plotted all the slope parameters, H ratio, T-slip, KY, T-slope, to make sure that the training and testing data were both well distributed within the input parameter space, as opposed to picking all your training data up here and all your testing data down here. So as I mentioned, there were some tuning of the hyperparameters we had to deal with. In the end, maybe I'll gloss over this because I know I'm going a little bit long, but we came up with one hidden layer. You can see that the sigma does not continue to decrease after about 3 to 4 neurons. So neurons in that middle layer. So we used 4 neurons, and we saw that the sigmoid function, activation function, here's the sigmoid in black, did the best job, just a little bit better than hyperbolic tangent. And so we went with the sigmoid function. So then we trained the model, and it looks complicated, but in fact, this is a relatively simple ANN models. We have all the biases and weights published in the paper because we only have 1 hidden layer and 4 neurons. But the key is it takes the inputs that are actually normalized. Remember, multiplies times the weights, sums those up, adds the bias, puts it, that's the sigmoid activation function. So Z goes in there, comes out, the sigmoid number, the value that comes out of the sigmoid function is phi. That goes into this output layer with its biases and weights. And each of those come together into predicting the displacement. And actually that equation can be written out here, but we made it easy on you. We have published in DesignSafe not only a Python Jupyter notebook that can do this analysis, you can do the ANN prediction, but we also have published the 50,000 displacement values and the slope, T-slope and KY and PGV and the input finite element models. So if you want to build off this work, if you have an idea of how to do a better statistical analysis, just take our data, analyze it. Please cite our data set and run with it. So this is the idea of being able to accelerate research discovery by publishing data, not just results. So this is, I leave you with one thing. If you're not a seismic slope stability data person, publish your data, publish your scripts so that other people can build off, cite what you did, you still get credit, but can build off that work. And I think that will just explode how our research can move forward at a faster and faster rate. So having developed the model, we can look at assessing it. As I mentioned, we do it on the testing data. So we've got this is the computed displacement from the finite element analysis versus predicted. So it's a cloud, of course, but it's very much around the 1-to-1 line. We have a sigma that is relatively small, 0.4. Just to compare for a specific slope, how would the classical regression versus the ANN model do? What you can see here is we kind of decided to go with a simpler linear relationship for the classical model. The ANN model, at least at the slope level, allows us to have some curvature. So to be honest, you're going to see there's modest improvements relative to the classical model in terms of standard deviation, but there are some absolute benefits to the ANN model. But the thing is, you're not doing a ton better if you look at each of these ones, except maybe at an individual slope level, except maybe near the two tails. We computed the sigmas again, the tau and the phis. In fact, at a slope level, because of the ability to kind of fit that curvature, the tau for the ANN regression was actually smaller than the classical model. So these are the etas. And the phis, though, are about the same. It's about 0.4. Again, we have a predictive model for phi. And this is probably the crux of it. How much did the phi change? This is the ratio of the phi for the ANN model to the classical model. Most of the points are below 1, not all of them, but it's a very modest improvement. Look at, I broke all my rules. I didn't put this vertical axis to 0 so you could see something. It's 2, 3, 5% reduction in phi. So tau decreased about 25%, phi decreased about 5%, but overall the sigma only reduced between about 5 and 10% compared to the classical model. But one thing that's nice, and one thing that is kind of difficult about the classical model, is that we have this discontinuity. If you are H ratio of 0.59 versus 0.61, remember that's where we define shallow versus deep, you get different predictions. Well, now because H ratio was one of our input parameters, you can see that now we have a smooth transition where here's the deep slip surface, here's the shallow slip surface. So you can see on the two end members, the results are very similar to what we had previously. So this is displacement as a function of Ky. Well, it doesn't say the PGV, but I'm pretty sure this is PGV of 100 centimeters per second. And so now you have a more continuous variation of the predicted displacements with H ratio. And again, seeing how things compare on the right-hand side here for the ANN model, we can see for the deeper slip surfaces, say at 1.6, T-slope really doesn't matter. Even though all these models had T-slope on the input, the ANN model could identify the trend that T-slope does not affect, because these are different T-slope values, don't affect the displacement. But for shallower, smaller H ratios, shallower slip surfaces, T-slope matters. Okay, so again, I didn't program a regression functional form in the ANN. All I dealt with the weights and the biases. And the ANN model was able to identify similar trends that we found in the classical model and even improve upon those trends. So just one slide in conclusion here. The seismic risk assessment for earth dams and slopes requires a fragility framework that importantly incorporates all of the uncertainties and variabilities. And while I think we as geotechnical engineers have done a pretty good job of developing demand models, from whether mostly numerical simulations, those surrogate models, I think we need to all think a little bit more about how we can then take that and really predict the damage state. And that's looking at the capacity models from field observations. You know, the Pels and Fells and Sway's good data sets are 20 years old now. No one has gone out and taken all those gear reconnaissance reports and where we estimated settlement for different dams or levees. I think there's definitely a need to put all that stuff together in a data set, publish it in design safe, I might say, so that all of us can use it and build better capacity models. And then I did show you also the demand models we've developed for slope movement that we computed, where the slope movements were computed from finite element analysis. We have found PGV is the most efficient intensity measure to predict displacement. I am a big fan of peak ground velocity, that is for sure. And I think because it brings in intensity and frequency content, I think it's a really great ground motion parameter for this problem. We saw that we developed models where KY of the slope, the period of the slope, and H ratio all influence the displacement. And the ANN model was able to more fully capture data trends across the input variables without having to come up with a complex functional form. And so with that, I will see if we have any questions. And I want to thank you all for your attention, and thank you, Felipe, for inviting me to give this presentation.
Thank you very much, Professor Rathje. It was a great presentation. Particularly, I really like this topic. I wonder if there are, as Professor Rathje asked, is there any question in the Zoom room among the attendees that we have today?
I don't want to call out any of my friends who might be in there.
Yeah, Dr. Verdugo is there. Marcelo
Hi,
is
Ramon.
Hello, nice to see you again. Okay, I have a question. Very simple.
Okay.
You have defined the T slope, or I don't know, that should be, or something like T slope means the period of the slope, because it's 4h divided by shear wave velocity.
Mm-hmm.
But in the case of a slope, I don't think that represents the period of the slope. But as a parameter, it seems to work.
So I would argue if we were trying to represent like say some sort of tuning ratio, the period of the slope to the period of something in the ground motion, you'd want to be sure that whatever, maybe you would actually want to do a modal analysis, right? An eigenvalue analysis, and actually find out what is the actual period of the system that we are analyzing, right? But in this case, I think of T slope as representing the flexibility of the slope. And the flexibility of any soil deposit, slope or not, is its height and its stiffness. Doesn't matter if I put a 4 in front, a 2.6 in front, or whatnot. And so that's where I think it's okay.
For me, it should depend on the angle of the slope.
I mean, certainly, but it depends. What are you trying to represent? I mean, and would we have gotten a better result if we tried to incorporate that? We didn't look into it, but we could. I mean, like I said, we could have done a modal analysis and said, what is actually an eigenvalue analysis? What is the natural frequency of the system we analyzed? But we did, but we didn't do that. But it certainly could. It certainly could.
Anyhow, it works. That's fine. That is the good point.
And
Very
I
nice
think,
work.
and the reason I think it works is because you saw that deformations were not just localized right at the slope face, they were distributed deeper and further back. And so the impact of the slope angle was probably minimized. And that's
Yeah.
why the height and the shear and the stiffness was most important.
Very nice presentation. I enjoy it. Thank you very much.
Thank you, Ramon.
Yeah, it was a great talk. It seems that we have some questions from the YouTube audience.
Oh, great.
It seems to me that it's a Japanese audience.
Oh,
It's
okay.
Japanese. The person says, I wanted to know how the ANN was performed, like which software or where the networks were programmed.
Yes.
The person is very interested in the application of this analysis in geotechnics. I think this is a this is a great tool. This is a great tool that it cannot be applied only to slope, but you can apply it to many other geostructures, right?
Right.
So in this context, the colleagues here, he wants to know how the ANN was programmed.
Sure. Let me talk towards that, because it allows me to promote Design Safe a little bit more. So my PhD student, Young Q, used the scikit-learn package, Python package, Keras and TensorFlow. So these are kind of AI toolkits, all done in a Jupyter notebook, running on Design Safe. And for the person out there, if you go to our Design Safe data set, not only do we have a Jupyter notebook that does the model predictions, we have a Jupyter notebook that shows you how we trained the ANN model. And so you can take a look at that and get all the details, because like most professors, I don't know the details. The student knows all the details. But I do want to just say this is another way that we really want to encourage data or just research, accelerating research, as opposed to me saying, well, go read it in a book and come back and ask me some questions. You can actually look at a script that we developed, published, and build off of it. And then when you do your great ANN model, you can then publish it, cite that you built off of our script, and go from there. So I'm excited about that. In fact, the other day, Albert Kotke, a former PhD student, he saw the paper, and he tried to just code up the ANN from what we gave in the paper, and he interpreted something wrong. And I said, go check out the data set, the Jupyter notebook on Design Safe. He said, oh, now I know what I did wrong. And so it really helps also reduce errors going forward. So we're really promoting AI and machine learning through Design Safe. We had a boot camp and a workshop right before COVID, February 2020. There's a report and some materials on Design Safe too, and I would be happy to answer any emails about that. I guess my last comment on ANN and machine learning is the data are so important. The data, making sure the data is well distributed in the input variable space, and that because we even saw some problems where right near the edge of the input parameter, you cannot extrapolate an ANN, any type of machine learning model, obviously, because it's so data specific. But in one area where we didn't quite have enough slopes in that parameter, things start to just look a little strange in that parameter space. So you really have to think about your data and the limits of the model that ultimately comes out based on the data that goes in.
Nice, very nice, very, very nice. Yeah, Jupyter and Python are powerful tools, are really powerful tools.
Yes, absolutely. and we're really banking on them to really push things forward. It really is a nice middle ground between, what you can do in, say, Excel or something like that. It's like MATLAB, but it's open source, which I love. And even what we're doing with Design Safe, you can even submit jobs to the high performance computers through Jupyter, so that you don't have to, sometimes it's a bit intimidating. Ooh, am I getting on the command line of this, big system? We're trying to really lower the bar to people using high performance computing.
How big are these supercomputers? What is the size of these supercomputers that you have? It seems, how many, at least here in Chile, we call them nucleus, and like processors that you can you can have running in parallel. How many of those do you have over there in Texas?
Too many to count, I think.
Okay.
And I don't know the numbers off the top of my head, except I will tell you this, is we have at TAC, so TAC is the Texas Advanced Computing Center. When I started working with them as 6 or 7 years ago, there was Stampede. Then we built Stampede 2. You'll notice there's a trend in the names here, Stampede, Longhorns, all those good things. But they're right now designing and building Frontera, which is the next generation academic supercomputing cluster. And if you just go on TAC's website, you'll learn more about it. But the number, they've got CPUs, they got GPUs, thousands and thousands and thousands of processors and nodes that are available. And they're doing they were part of simulations that people are doing for the, black holes, and there's some great stuff that they're doing. But it will be basically one of the top supercomputers when it's complete in a couple of years.
Nice. So once you press enter, how much time it takes for the computer to complete the task?
Well, it depends on how optimized your code is. It also depends
sure.
There's also a queue, you can imagine, right? The roller coaster may be fast, but there's a long line to get on the fast roller coaster because everyone wants to go on the roller coaster. So it depends. But in some cases, what's beautiful is, like, for our analyses, every of those 50,000 analyses were independent of one another, right? Because it's a slope model and a ground motion. It doesn't matter what the other slope model and ground motion is doing. So we could run those all at the same time rather than to do them sequentially. We could do them in parallel. We did have to break them into chunks, but we broke them into chunks of several thousand at a time. Again, I don't know the exact numbers, but it is fast. And we have a big staff to help people try and optimize what they're trying to do.
Nice. We have some more questions, Professor. James Adinata, he says, well, he congratulates you for the great talk. It was a great talk. And he says, thanks for the great talk, Professor. Would you please remind us about advantages of PGV over the others IMS that incorporate both duration and amplitude, such as the area's intensity and CAV?
Duration, I think duration matters. And particularly, when you think about Chile, you think about subduction zone events, right? And of course, subduction events have longer duration. I am surprised that PGV does so much better than areas intensity and CAV. Both of them, all three of them, represents some sort of integral over the acceleration. You could imagine areas intensity has a problem because low intensities still continue to contribute. But that's what CAV is attempting to incorporate. To be honest, why does PGV work? I think it's because it does have a peak. It's a peak value. So I think it better represents the intensity and frequency content. I do think it has a duration issue, right? Where it's never going to be able to model subduction events. You'd have to create a subduction event model, displacement model. But because Arius intensity and even CAV, you can stay moderately, at moderate intensities, and still just if you go on longer, you get a bigger Arius intensity in CAV. I think that's part of the reason it doesn't do well, because it doesn't have a PGA or a peak value to it that happens in the most intense part of shaking. And I really appreciate this question because I hadn't thought about all the details of why. But if I go look and see, Arius intensity and then adding PGA will do better. And because it brings that intensity information. But if you can do it in one intensity measure, then I'm certainly all for that, because I've developed models that are a function of PGA and PGB, and then it gets really complicated on how to deal with we're trying to predict those together and their correlation. It gets more complicated. So if you can stick with one intensity measure, I think it's better.
Nice, very nice. We have one more question. Well,
okay.
I have some questions. They are really quick questions. But first, one person of the audience, the colleague that did the first question,
okay,
he says, "Your talk is amazing. You did a great work. I have been following you since 2018, since the Sochije event."
Oh yes, right. I had a great visit in Chile.
So thanks again. That's what the colleague said.
That really makes me feel very, very nice. I really appreciate those comments.
Professor, it seems that we don't have more questions from YouTube. I would like just to ask two quick questions.
Okay.
In these models, the models, I don't recall it very well. The phreatic line was not considered, right?
No.
It's dry. This is dry, right? Okay.
I'm no liquefaction, no nothing.
Exactly.
Keep it simple. Yeah.
Exactly. And about that's very interesting when you talked about the weighting functions. What was your criteria to determine the weighting functions? Because that's the key, right? That's the key to determine the models.
Yes. You in the ANN model. Yes.
Mm-hmm. Yeah,
so
the weighting function.
This is the beauty and the danger of these pre-packaged packages, right? There's a slope gradient descent approach. I mean, it's like a statistical regression. And it is trying to minimize some sort of objective function. And that's how it finds the weighting functions. So I didn't have to put any criteria.
I see.
It's all internal to the solution. Yeah.
I see. The last question. What is the next step with so much data that you have?
So I really want to understand physically better what is going on with those shallow slip surfaces, because it's still, I'm like, how can KY not matter? Why is that displacement versus KY flat? So I have a new postdoc working on design safe, and he and I are going to be taking a closer look. We're going to use OpenSea, see if we get the same results. We're going to try different ways to model things to really kind of understand the physics of what's going on. So at least within this framework, that's where I sit. And then we're also doing, this is related, but not with all the 50,000 analyses. We are working on some of the dam stuff, trying to take that all the way to fragility in Texas, because we're interested in understanding dam fragility in Texas, because now we have these earthquakes and they're, can be a magnitude 5.5, all of us, and these are not necessarily, they're not dams designed for earthquakes. So that's another thing that Jing Wen, my student, is embarking on right now. So.
Very nice. Thank you very much.
And do you mind if I say one other thing just about all this AI and machine learning? Because I know a lot of students are interested in that. And I will say, 20 years ago, I was absolutely a skeptic. 10 years ago, I might have absolutely been a skeptic. Now, I obviously I've been influenced by working with all the really smart people at the computing center and TAC. And I know a lot of us, or a lot of older people, I guess I'm in the older people realm, feel like, well, I don't want this black box replacing the engineer. And I completely appreciate that. And I do think that shows why it's important for you to have domain knowledge to use those tools. But so I do not think AI models will replace the engineer. But I do think at some point, engineers who use AI models will replace engineers who don't and don't know how to use them. So I really just want to encourage all the younger people just to understand these new advances. Don't be afraid. I mean, I knew nothing about this 22 years ago. And, you know, collaborate with someone who knows what they're doing in this new area. Bring your expertise in. And that's really where we push the profession forward. It's those collaborations of different fields. And so go ahead, go do it.
I absolutely agree. I absolutely agree. I wish I had more time to get into the code, right? Because
Exactly.
it's Jupyter, it's Python, and what amazes me is how the young are able to handle all of this so naturally, and then they can have a computer talking with three softwares different.
Yep.
They are all open source, and they do marvels, right? They
Yep.
do marvel.
Absolutely.
It's amazing. Yeah,
it is, but I
absolutely
also, but us older folks do still have a role, because we can look at results from all that fancy analysis and say, nope, something's
Exactly.
wrong. I don't know
Yeah.
what's wrong, but it shouldn't be doing that. And
Exactly,
either
yeah.
explain to me why it's doing that or fix it. I've found that happens too. And that's the beauty of working together,
Exactly.
right? You know, having that
agree.
experience and then having the skills that the students have. It's a lot of fun.
I agree. Absolutely agree. Thank you very much. It was a great talk. It was an absolutely hot topic. It's absolutely of utmost importance. And so I don't know what time is this, but it's actually it's 7:30 here.
Oh.
So it's been a long talk, and we appreciate the time you took for being here with us. Thank you very much. And we appreciate that you also took the time to share your expertise and knowledge with us, Professor Rathje. I don't know if Carlos is there, but we need to stop the broadcast through the YouTube channel. So we will stay here 2 more minutes with Professor Rathje, and we say bye to the audience.